Welcome to The Deep Dive. We're the podcast where we really plunge into some groundbreaking ideas, trying to pull out the insights you need to stay ahead.
Huh?
And today, wow, we're tackling something huge, a challenge that's growing faster than most of us probably realize. We're talking about the sheer, insatiable energy use and the, frankly, exploding ecological footprint of our digital world. Just think about what modern computing can do. It's incredible, right? But training those big machine learning models, they can chew through megawatts of power for just one training run. And then you got things like the Frontier supercomputer, right now one of the world's fastest. It operates at, get this, 21 megawatts. It's just mind-boggling.
It really is. And that figure, 21 megawatts, it paints such a stark picture.
Exactly. Now hold that number, 21 megawatts, in your head.
Right.
And compare it. Compare it to the human brain. This biological supercomputer you've got performs comparable operations, maybe even far more complex ones, right? Processing information, learning things, creativity, all on about 20 watts.
20 watts.
20 watts. Less than a dim light bulb. The difference is just, it's almost unbelievable, isn't it?
Completely.
And that massive gap, it really sets up the central mystery and I guess the big hope for where technology could go. So have you ever wondered if there's just a fundamentally different way to compute? I don't mean just a faster chip or, a slightly better algorithm, but something that doesn't just mimic the brain, but is actually, well, biological, alive. Well, today, that's our mission. We're diving into a truly radical idea. It sounds like science fiction, honestly, but it's grounded in some really cutting-edge research. We're talking about a living, potentially self-powered computing platform. It's called the Symbiotic Quantum-Fluidic Mycoid Biocomputer. Quite a mouthful, SQFMB for short.
SQFMB, yeah.
And we're going to unpack how insights from, well, all over the place, organoid intelligence, quantum biology, believe it or not, fungal signaling, these things called iontronic memristors, even ancient geochemical energy, how these can all sort of collide to create something, well, completely new. It's a journey into what it means for a computer to be alive, and maybe, just maybe, how that's our most sustainable path forward. Okay, let's unpack this.
What's fascinating here, and really what makes this whole conversation so urgent, is that this isn't just some, academic thought experiment for the distant future.
Right.
It's a critical challenge right now for the whole planet. You mentioned the energy use. Think about the numbers.
Yeah.
Global data centers, they're already pulling over 3% of the world's total electricity.
3%, that's huge.
It is. And their greenhouse gas emissions, they're getting close to, and in some projections, might even exceed the entire aviation industry.
Wow.
So this isn't just about tweaking efficiency, shaving off a few watts. It's about a fundamental shift. We need sustainability in computing. If you look back at how computing evolved, right, from mechanical calculators, vacuum tubes, then transistors, silicon chips, each step was a huge leap.
Right, in power and shrinking the size.
Exactly. But the basic idea, this sort of binary electronic switch, hasn't fundamentally changed that much. This SQFMB idea, it's not just improving silicon, it's rethinking what a computer even is by using life itself.
Moving beyond just copying biology to actually being biological.
Precisely. Embodying it.
And when you lay out the scale of that energy problem, yeah, it's immense.
Let's dig into that a bit more, this computational conundrum, because it really does affect everyone. That Frontier supercomputer, 21 megawatts. That's enough power for, what, a small city, like 25,000 homes?
Roughly, yes.
Yeah.
An enormous draw. And it's not just the supercomputers, it's training those big AI models too, right? The ones behind language tools, image recognition, all that stuff. You said megawatts just to train them. That's sustained power draw, not just a blip.
Sustained, exactly. These are energy-hungry processes.
So think about it. Every time you use some clever AI tool or stream a movie or do a complex search or even just scroll through your social media feed, there's this hidden energy cost and it's growing, like exponentially. It's like having this amazing super fast sports car, but it just drinks fuel at a rate that's completely unsustainable if everyone drove one.
That's a good analogy.
So the question is, how long can we keep this up? Ecologically, with emissions, and just economically, the cost of electricity, it feels like we're hitting a wall, but it's a power wall, not a speed wall.
And that power wall, that energy bottleneck, combined with our ever-growing demand for smarter systems. That's exactly why the human brain is such an incredible template. It's more than just, inspiration. It's like a functional blueprint for a more sustainable way to compute. The brain's genius isn't just raw power, though it has plenty. It's how it processes information. It's massively parallel. Billions of neurons firing together.
Handling everything at once, basically.
Right. Sensory input, memories, thoughts, all in real time and so efficiently. And crucially, It's amazing at data efficiency. It learns from just a few examples. Think about a kid recognizing a cat after seeing maybe one or two.
Yeah, compared to AI needing thousands, millions of
Yeah.
pictures.
Exactly. It's a massive difference. It shows a limitation in current AI, relying on brute force and huge data sets. And then, of course, there's that energy efficiency, that 20 watts you mentioned. For perception, thought, creativity, self-awareness, it's just staggering next to digital machines.
It really is.
That efficiency isn't just a nice feature. It shows a totally different approach to processing information, one that silicon just can't mimic effectively. The brain's built to save energy. It's the ultimate model for sustainable intelligence.
So it's clear we need something radical, a whole new way of thinking about computation, which brings us right to the core of this deep dive. These five really different, almost unrelated fields that, when you combine them, form the basis for this SQFMB. This isn't just one clever trick. It's like a symphony of ideas from places you'd never expect to see together. It really shows the power of, interdisciplinary thinking.
Absolutely.
Okay, pillar one, organoid intelligence, OI. Now, when we say miniature brains, what are we actually talking about? Imagine these tiny 3D brain-like structures. They're grown in labs from human stem cells.
Yeah.
And they're not just blobs of cells. They actually recapitulate, basically copy aspects of real brain development. They grow, form connections.
Neural connections, yeah.
And they can even show basic forms of learning and memory. It's pretty wild. So this field, organoid intelligence, is all about harnessing these things as biological computing units. Researchers are thinking, okay, what if we link these two inputs and outputs, train them with biofeedback, machine learning, like AI, but with living tissue, the big vision, networking lots of these organoids together, creating intelligence in a dish systems, a totally different, maybe super efficient way to compute living hardware.
The potential is definitely exciting, no doubt about it. But we absolutely have to talk about the hurdles, and maybe even more critical, the ethics involved here. Biologically, just growing them big enough is tough. Once they get past a few millimeters, the inside the core often starts to die off. Necrosis.
Why is that?
Just lack of nutrients and oxygen getting to the center. Diffusion limits. So getting them stable, mature, complex, it's really challenging. And then trying to connect these soft, living things to our standard, rigid electronics. That's not simple either. You need new ways to read signals, new algorithms, new hardware that won't, damage the tissue.
Right, bridging the gap.
But beyond the tech stuff, OI really pushes us into some deep ethical water. This raises an important question. As these organoids get more complex, what about sentience, consciousness, moral status?
Yeah, that's the big one. Do they feel anything?
Exactly. At what point do we have to worry about their welfare? This means we need ethics baked in from the start, an embedded ethics approach, not just thinking about it after a problem comes up.
So these challenges, technical and ethical, they kind of push us to look for other pieces of the puzzle, right? Technologies that can help out.
Precisely. They prompt the search for complementary technologies.
Yeah. Which leads us perfectly to pillar two. This one's pretty out there. Quantum biology. Specifically, these things called Posner molecules. Now, these are specific clusters of calcium and phosphate. Calcio is the formula, but think calcium phosphate clusters. The hypothesis in quantum biology is that these molecules might be able to preserve nuclear spin entanglement, that weird quantum link between particles inside biological systems.
Inside the warm, wet brain environment, which is the really tricky part.
Right. If they could do that, maybe it allows for quantum information processing in the brain. And here's where it gets really interesting. There's this potential link to lithium, the drug used for bipolar disorder.
A mood stabilizer.
Some scientists speculate that the difference in nuclear spin between lithium isotopes might actually be why it works, how it affects behavior.
It's a fascinating, though still very speculative connection.
So, if these Posner molecules can protect entangled phosphorus spins from decoherence, stop the quantum state collapsing, it opens this mind-bending possibility. Could quantum effects be subtly influencing how our neurons signal? Maybe underpinning memory or even consciousness?
It's an incredibly audacious idea, bridging quantum mechanics and biology.
It really is.
But it's absolutely vital to stress, again, how speculative this is right now. The theoretical models are interesting, yes, but finding concrete experimental proof of Posner molecules in vivo, inside living things, that's still proving very, very difficult.
Hard to detect, I imagine.
Extremely. And we just don't know how long quantum coherence could realistically last in that noisy, warm, wet brain environment. Usually, quantum states are super fragile.
Right, they decohere quickly.
Exactly. But If these quantum resources do exist, and if we could somehow harness them or even engineer them into biological systems, it might open the door to totally new kinds of computation, error-corrected, maybe ultra-low power happening within living tissue. These Posner clusters, if they pan out, could potentially act as a kind of quantum memory layer, augmenting classical neural processing.
Quantum memory. Wow, okay, that's deep. Let's shift gears now from the super theoretical to something more earthy. Pillar 3, fungal electrical signaling. Most people know about the Wood Wide Web, right? These huge underground mycelial networks connecting trees, sharing nutrients, water, signals.
The ecosystem's internet, in a way.
Well, it turns out these fungi, these filamentous fungi that make up the mycelium, they can actually generate and send electrical impulses through their hyphae, those little thread-like structures.
Action potential like spikes, remarkably similar to neurons.
And the structure of these networks, these mycelial networks, they look surprisingly similar to neural networks, don't they?
They really do. That structural similarity is striking. It suggests, perhaps, some convergent evolution in how information gets processed and transmitted across different life forms.
Could we use that then?
Well, the analogy holds up pretty well. Even without distinct axons like our neurons, these fungi show these voltage spikes. What they mean exactly, the code they're using. We're still figuring that out. It's hard to study because the hyphae are microscopic and the networks are delicate. Sticking electrodes in can easily damage them.
Okay.
Plus, the signals travel pretty slowly compared to our nerves, which suggests they might be acting more like analog integrators, processing things over longer times and larger areas rather than fast digital signals.
Slower, but maybe useful for different things.
And that's their potential strength for this biocomputer idea. They offer this incredibly resilient, self-healing, three-dimensional biological wiring. Think about it. You could potentially use them as an organic wiring harness. Maybe even weave the organoids into the fungal scaffold. The fungi could deliver nutrients, water, solving that diffusion problem we talked about with organoids, and maybe those slow electrical potentials could modulate the organoid state over time. It's organic integration.
Living wires. That's incredible. And speaking of bridging biology and electronics, Pillar 4 sounds like it fits right in. Iontronic fluidic memristors. These are really unique, brain-inspired, but they work differently than silicon. Instead of electrons in solids, they use the movement of ions, charged atoms in water, to mimic synaptic plasticity.
That ability of brain connections to strengthen or weaken, which is fundamental to learning.
Right. So how do they work? They're basically tiny, tapered microchannels, like mini rivers, inside a soft material. You apply voltage, and it causes salt concentration polarization. Ions move, creating high and low salt areas. And this changes the device's resistance, making it remember the voltage. Volatile memristive behavior.
Volatile meaning it fades when the power's off, usually.
Right. But the advantages. They're relatively cheap. You can make them in complex shapes using soft lithography, like biological 3D printing. You can tune their memory time by changing the channel shape. And the key thing, they use both electrical and chemical signals, and they operate in water, just like living cells.
That compatibility with aqueous environments is definitely a huge plus. Researchers have already shown they can do things like classify handwritten digits using these fluidic channels. So the potential for computation is there.
Cool.
But yeah, there are limitations. That volatility you mentioned means they often need constant refreshing. Controlling the movement of different ions, especially in large networks, gets complex. Scaling them up faces challenges, noise, crosstalk between channels, making them reliably.
Like any new hardware, really.
Pretty much.
Yeah.
But their ability to mimic synapses using ion flow and liquid, that makes them incredibly promising for interfacing directly with living tissues like organoids. They speak a similar language, chemically and electrically.
A natural bridge. Okay, Pillar 5, this one goes way back. Geochemical hydrogen metabolism. Ancient Earth energy. Yeah, this is wild. Research suggests that way back on early Earth, in those deep-sea hydrothermal vents, iron sulfide minerals, things like maconite and greigite, naturally produced hydrogen gas, abiotically, meaning no life involved, just geology.
Purely geochemical reactions.
And this hydrogen, it might have fueled the very first metabolic pathways. It sustained these ancient microbes called hydrogenotrophic methanogens.
Microbes that could use hydrogen to turn co-uro into methane, basically making energy.
Exactly. This process might have provided the energy for the first cells to even get going. And it's not just ancient history. Modern black smoker vents still do this today. It's like a natural self-sustaining energy engine.
And that ancient process gives us this incredible blueprint. We can actually replicate these conditions in the lab, in chemical gardens, and generate hydrogen sustainably. Hydrogen is a clean fuel, right? And a key electron donor for lots of microbial metabolisms.
So for the biocomputer,
It means the potential for a completely carbon-negative, self-powering energy source. No external electricity needed. Imagine a computer literally feeding itself from simple chemistry, like early life.
that's revolutionary.
It is. Now, there are challenges, of course. Getting the hydrogen yield right, scaling it up, controlling the reactions. That requires engineering.
Mhm.
But the basic principle, it offers a path to truly autonomous, sustainable computation, totally off the grid.
Okay, 5 pillars: organoids, quantum biology, maybe fungi, iontronics, and ancient geochemistry. Incredible mix. So how do we put these pieces together? This isn't just sticking things side by side. It's about creating a truly symbiotic system where the limits of one part might actually be, well, useful design features for the whole thing.
Exactly. It's about integration. The whole SQFMB concept has 3 main goals. 1,
Mhm.
ultra-low power adaptive computing, way beyond silicon. 2, a sustainable self-regenerating energy supply, ideally carbon negative. And 3, critically important, an ethically embedded design right from the start, addressing those consciousness concerns proactively.
All right, let's visualize this layer by layer. Starting at the bottom, the powerhouse, the geochemical energy module. So we've got this reactor, like a chemical garden, with iron minerals and sulfate solutions. And it's constantly precipitating more minerals like MXene and greaseite.
Releasing that abiotic hydrogen as it does so.
And that hydrogen feeds special microbes, archaea, and bacteria lining the reactor. They use it, plus COs, to make organic acids, acetate, formate, basically food.
Using the acetyl-CoA pathway, yeah.
Yeah.
Super efficient ancient metabolism, turning CoA into food for the rest of the system.
And you mentioned mimicking hydrothermal conditions with heat and mineral gradients.
Right, to keep the process stable and robust. It's like a tiny, self-contained ecosystem generating power and food.
Okay, built on top of that energy base, the mycelial scaffold, the fungal network.
Exactly. A dense network of fungi, maybe something like neurospora, grown inside a 3D printed porous structure surrounding the chemical garden. Its main job, distribution. It moves the nutrients and water from the energy module to everything else. It's the living wire harness.
And it sends signals too.
Yes, those slow electrical signals we talked about. They can modulate the microbes in the energy module and also the organoids further up. If we connect this to the bigger picture, this scaffold is key for self-organization and adaptation. It provides structure, it helps with fluid flow by secreting polysaccharides, and it even insulates the iontronic circuits, nature's integrated circuit board.
Wow. And nestled in that living circuit board is the iontronic computing layer. Those fluidic memristors again, but now built right alongside the fungal hyphae. Tiny microchannels filled with saline solution, coated with conductive polymers, maybe calcium phosphate nanoparticles, and voltage pulses, maybe from the microbes, maybe from outside, create that salt polarization, the memristive effect. They act like synapses.
Forming an iontronic reservoir computing network. Reservoir computing is great for processing real-time signals efficiently because the complex network does the heavy lifting.
Like ripples in a pond encoding information.
That's a good way to think about it. And you can tune the memory time by changing channel geometry. Plus, the hydrogen metabolism helps refresh the volatile memory, keeping it active.
Okay, so energy wiring processing. Then at the periphery, the organoid intelligence nodes.
Right. The brain organoids themselves, cultured on microfluidic chips, but embedded within that mycelial network. They get nutrients from the fungi and perfusion systems. And 3D microelectrode arrays let us record their activity and stimulate them.
And the ethical safeguards. You mentioned keeping them below conscious perception.
Absolutely crucial. Engineered from the start to lack structures like full cortical layering associated with higher cognition. The goal is computation, not consciousness.
And the quantum bit. You modify them to make Posner-like molecules.
That's the idea. Genetically modified to produce those intracellular calcium phosphate clusters. The theory is this could stabilize nuclear spin coherence, potentially improving memory, reducing noise, acting as a quantum-inspired memory buffer.
Quantum-enhanced brain organoids. Okay. And finally, tying it all together. Interface and control. How do all these layers talk? The iontronics connect to organoids via electrodes and chemical gradients. The fungi connect everything.
Exactly. And for output, you have a readout layer, maybe conventional electronics, maybe other organoids translating the ion currents and organoid spikes into something usable.
And the whole thing is protected.
Encased in a semi-permeable membrane for gas exchange, but protection from contamination. Plus, sensors for pH, temperature, vibration, feedback into the ionotronic layer for adaptation. And crucially, a digital twin, a virtual model, monitors system health and ensures the organoids stay non-sentient. It's a closed-loop control system.
Incredible architecture. So how does it all work? The operating principles. Energy first.
It's designed to be self-sustaining. Hydrogen from the base fuels the methanogens. They make metabolites. Fungi transport these to the organoids for food. And the ionotronic channels use the ionic gradients from all that microbial activity. So, yeah, autonomous operation, no external power needed once it's running.
Imagine that, a computer that feeds itself.
It's a radical concept.
And information processing. How does it think?
It's multimodal. Environmental signals change the chemistry at the base. That creates ion patterns flowing through the ionotronic reservoir network, processing temporal signals. The fungi carry slower, contextual signals. The organoids get input from both, learn via plasticity, and maybe use those Posner clusters for enhanced longer-term memory retention, cutting through noise.
And the outputs.
Could be changes in its own metabolism, growing new fungal connections to rewire itself, or sending electrical signals out to other devices. It's dynamic.
And that leads to adaptation and plasticity. It's not static.
Not at all. Self-organization is key. The mycelia grow and reorganize. The ionotronic channels adapt their memory. The organoids learn.
With feedback loops adjusting everything.
Right. If a task needs longer memory, maybe it grows longer ionotronic channels or makes more Posner clusters. It's like the computer's literally growing and evolving its own hardware based on what it needs to learn or do.
A living, evolving machine. Okay, so after all that, what could this actually do? What are the potential applications?
Well, several exciting possibilities. First, ultra-low power sensing and control. Because it powers itself, you could put these things anywhere. Remote environmental sensors monitoring soil, forests, maybe even seismic activity, autonomously for years.
Wow. Yeah.
Second, biological coprocessors. You could interface them with regular computers to handle really complex, energy-hungry tasks, advanced pattern recognition, anomaly detection, adaptive control for robots or smart infrastructure. Let the biology do the hard, adaptive stuff.
Makes sense.
Third, it's an amazing research platform for studying the origin of life, how metabolism and information co-evolved, and maybe even probing those quantum effects in cognition via the Posner clusters.
A testbed for fundamental questions.
Exactly. And fourth, just as a tool for education and art, imagine an interactive installation that literally grows and thinks, responding to its environment or people.
Yeah.
A powerful way to engage the public with science, ecology, ethics.
An art piece that thinks, that's cool, but this brings us to a really critical point. Scenario mode. With something this powerful, this, alive, we have to think about the highs and lows.
Yeah.
This raises an important question. What are the best and worst case scenarios here?
Right. Best case, everything works beautifully. Stable hydrogen production, robust fungal networks, organoids stay non-sentient but become incredibly good at pattern recognition, maybe boosted by that quantum coherence. They learn complex things fast with little data. We use them for ecological monitoring, optimizing greenhouses, maybe predicting earthquakes, all sustainably.
Carbon negative computing.
Exactly. Reducing emissions, maybe sparking new biocomputation industries. And all under strict ethical oversight, ensuring non-sentience, preventing misuse. It's a vision of ecological intelligence working with us.
Okay, that sounds pretty amazing, but the flip side, where's
The biological nature brings risks. Uncontrolled growth, contamination leading to chaos. What if the fungi become invasive?
Yeah, that's concerning.
A deeper worry. What if the organoids do inadvertently achieve some level of sentience despite safeguards? Huge ethical crisis right there.
Absolutely.
Or maybe those quantum effects, if real, interact weirdly with external fields, making outputs unreliable. And misuse is always a concern with powerful tech. Covert surveillance using biological processing. Bioweapon development. Without strong safeguards, it's possible.
And environmental risks. Releasing GMOs.
Could disrupt ecosystems.
Right.
And even basic safety. If the hydrogen builds up due to system failure, that's an explosion risk. These risks just hammer home the need for extreme caution. Strict containment, constant ethical monitoring, fail-safes like kill switches, physical isolation. You have to be incredibly responsible with living technology.
It's a sobering reminder. What an absolutely audacious vision, though. We've gone from the energy crisis of today's computers, a very real problem, to this potential future of living computation. Seeing how the SQFMB tries to collide organoids, quantum biology, fungi, iontronics, geochemistry to make something sustainable, efficient, adaptive. It's not just faster chips, it's using life itself, potentially running on carbon-negative power. So what does this all mean for you, listening? It suggests a future where technology isn't just about static machines, but maybe living, evolving partners, computers that are grown, not made, self-sustaining, maybe even integrated with the environment. It really challenges what we think a machine is.
It really does. This deep dive forces us to rethink those old boundaries between life and machine, energy and information. It challenges our whole concept of computation. By looking to biology's elegance and efficiency, the SQFMB points towards a future where tech is maybe more ecologically integrated, more sustainable. It makes us ask, what does intelligence even mean when it emerges from self-organizing biological networks like this? This raises an important question. How will we define computation and maybe even consciousness itself in a world where living systems might become our processors, and that line between biology and technology just gets blurrier and blurrier? It's a future with incredible promise, but also profound new questions.